Thank you, everybody, today for joining us on the Industries Application Drone LiDAR webinar presentation. I'm Ben Snyder. I'm Wingtra's Training and Certification Manager. I'm joined with Ted Strazimiri, who's the CEO of SkyDeploy, as well as my colleague here at Wingtra, Javier, who's the product manager here at Wingtra. Just a couple housekeeping things here before we get really into it. There will be an opportunity for some live Q&A. We do have somebody else, Andre, another colleague of ours at Wingtra, in the background who's monitoring those questions. So feel free to ask, and we will get to a section at the end where we will answer everything. And then finally, of course, we'll be sending out this webinar to everybody who's joined or was unable to join today. So Javi, over to you.
Thank you very much, and welcome everyone. I wanted to start today by sharing Wingtra's mission as an intro to the topic of today. The mission is to make it easy to digitalize the world with drones. Mapping drones are used across multiple sectors in mining, infrastructure, energy, land management, agriculture, or environmental sectors. Multiple applications can be benefited from the advantages of aerial data. Data can be collected, processed, and classified in multiple formats, depending on the intended use. We have orthomosaics, we have point clouds in photogrammetry, we have multispectral data that allows us to identify plants, to be able to select the right crops or the right spraying points for precision agriculture, or 3D reconstructions that are used in mining, in land management. But we also have LiDAR. We also have the point clouds that are provided from LiDAR data capturing. And this is what we will be focusing on today. So now I'm going to be handing it over to Ted, who is going to deep dive on these use cases and these applications of LiDAR data collection. Over to you, Ted.
Thanks, Javi. Thanks, Ben, as well. Great to be here with you guys. A little bit of a background on how we got here. About a month and a half ago, I started exploring primarily 3 VTOL platforms. And so you see them here. We have the Wingtra, the Quantum Systems Trinity, the Delta Quad Evo. And I've been getting a sense of what's going on in the LiDAR industry, and especially now that these payloads are really getting quite mature and the data is usually excellent across the board. But there's a lot of nuance in each of these, and that's what I wanted to share with everybody today, give you an overview of what I found, and also some more specific applications that LiDAR really works extremely well for. The Wingtra was the first one I received. So this is the Gen 2 with the LiDAR payload. Right away, my biggest sort of aha moment with it was just how easy it is to use. I think about 17 minutes into the training, I think I knew everything I needed to know and to go ahead and start collecting data. Very small package as well, quite logistically straightforward to use in the field. And so I collected a variety of data, and you'll see that data in these slides. That's what I'll be should be taking you through. We did a few missions where we did long corridors. In one case, we mapped 12 kilometers of road in one day with multiple platforms at the same time. So logistics is a big thing. And you really start to appreciate that once you start encountering more complex missions and once you've been in the field for a while. So I really do appreciate the simplicity and especially the small footprint of the Gen 2 Wingtra. But we want to talk a little bit about LiDAR. So I'm really, I love photogrammetry. That's how I started in this business. But LiDAR is similar but different. And you can see here on this slide that on the left, we have what you usually get from a photogrammetry flight, the series of photos with overlap. And then on the right, you see what you get from a LiDAR mission, a trajectory and a point cloud from that. The amount of data is kind of important to note as well. You can see how many flight lines photogrammetry would require for this area. And then also on the right, you can see the comparative amount of lines that had to be flown to collect with LiDAR. You can also notice that there's a few parts in that trajectory that are not mapping, portions, right? That's the aircraft's taking off and transiting to its first waypoint. But overall, it is very similar. Big difference, though, in efficiency. You don't need to do 75% overlap, for example. You can get away with much, much less, like 30 or 40%, and that allows you to cover a large area very quickly.
Can you please elaborate a bit more on this topic? So the
Mhm.
trajectory of the LiDAR capturing versus the photos in photogrammetry.
Yeah, I'll dive into that quite a lot because I think that's one of the main things that people have a little bit of trouble wrapping their heads around in the beginning when they get started with LiDAR. So you can see with photogrammetry, what we have essentially are these photo positions where we know approximately where the photo was taken. And then by using adjacent images with a lot of overlap, about 75%, we're able to calibrate where the photo was actually taken or estimate where it was taken in real space in that world frame. And then from there, we project those points that are matched between the photos into a point cloud. And that's what you see in the background. With LiDAR, it's direct georeferencing. So essentially, we have to know where the laser sensor, where the laser head traveled through space. And so that's what we refer to as the trajectory. It's sometimes the same as the trajectory of the aircraft, but in other times it may not be. It doesn't have to be exclusively tied together. But once we have that trajectory, then it's just a matter of painting those points in. And you can see in this is essentially just going through time and replaying how the data was collected. So we have points that are overlapping, but they come in these swaths. And you can think of it sort of like a spray paint, right? It's just you're spraying through as you're going, and where those points land, that's where you have them in your data set. But there's quite a bit of those points that are in areas that are not favorable to keep, such as the turns, right? Those are some pretty high dynamic forces in that moment. And then also the section where, in this case, with the Wingtra is the transit from that vertical takeoff to that forward flight. So we want to cut those out because it's just too much, and it actually can reduce the quality of the overall data if we leave it in. So this is what we get when we cut those out. So this is a very important step in the post-processing of LiDAR data. So we have our trajectory, we've painted the points in, and then now we need to clean it up a little bit. And you can see what it looks like when they are all together. So there's no fitting that needs to happen. These should just fit exactly where they belong because the trajectory was accurate. And everything starts from there. But you'll notice that there's areas where swaths may have overlap. So you can see the colors, for example, where purple and green on those woods overlaps. In those areas, we kind of need to be careful with LiDAR. So this is where the LiDAR post-processing kind of begins. And you can see in this graphic here, the purple and then the yellow. And if you look at the profile at the very extremities or very edge of that yellow swath, the precision of LiDAR does decrease because it has a much longer distance to travel. And so we don't need that information. We don't need those yellow dots there, those yellow points. So we can cut them out. And to do this, I use software called LiDAR 360. It's by far my favorite. And I'll give you a sort of a bit of a breakdown on the software workflow. But I think that this is quite essential, especially if you want the best results possible from your LiDAR data. And so once that's cut, it looks something like this. These strips are aligned as they were, but the sections of overlap have been reduced and cut out. And we have just what we need, essentially. If you don't do this, I mean, this can really vary by the sensor, but some sensors, especially how they scan, can be different. So this is an example from DJI L2 data. And so that uses a very different type of scanner, and the mirror, as you can see, it oscillates and creates this pattern. So if you don't do this cutting and cleaning of the data, then you may have less than optimal results, because there's just so many points kind of built up there. The flight that I showed you was about 16 minutes long. Oh, sorry, it was about 8 minutes long. And I also did a photogrammetry flight at the same time with the RGB payload. That was about twice as long. So in terms of efficiency, that overlap is one of the main reasons why you're able to complete things so quickly. And so that planning begins for me, and sort of the way that I use the Wingtra, and the workflow that I had was to plan on my desktop in the Wingtra Pilot app, and then take that mission, put it into the controller, and then from there fly the mission. Once the mission was flown, I would take the data from the LiDAR payload using the Wingtra LiDAR app is where we generate that trajectory. And you can stop there. You don't have to do anything else. The LiDAR app was actually quite feature rich in terms of the cutting and the splicing that you can do. But I always take it into LiDAR 360 to do some additional cleanup and post-processing.
And sorry, Ted, may I ask, because there are some people here that might be wondering, at this point, what level of technical expertise and skills are required to get to this data?
Well, so for step 1 and 2, so if you were to think of it as these are sort of the workflow on this page here, the planning is very straightforward. Now, you definitely should have some experience with drones, but it's not as complicated as you may think. The biggest takeaway, or the biggest difference between a VTOL platform like this and a more traditional multi-copter is that there's really like one button you press. You press takeoff and then you press land now. There's nothing that happens in between the flight. There's no controlling of the aircraft. It's all pre-planned, and that's really great because you're using this aircraft for very specific things like mapping, and mapping doesn't need manual control, and it doesn't need that much to happen while the vehicle is in the air doing its thing. So as long as you have the logistics figured out, you have the right location to take off from, and you've planned it with some training, the level of expertise, I would say, is pretty mild. That's required. Step 2, after you take that data off of the LiDAR sensor and plug it into your computer and process that trajectory like you see in that middle screenshot, that requires a little bit more. So you definitely have to have a good understanding of coordinate systems and where you want to end up in. I would say that 90% of the problems that people encounter in the field, especially with LiDAR, is not related to the LiDAR sensor or the workflow, but it's related to the base that they use. So the GNSS receiver that has to be on and recording data at all times. So usually that comes in the form of someone not placing it correctly, not entering the coordinates of that base station correctly, forgetting to log, all of these little things that can really spoil your data. And other than that, it's quite rare to see information be ruined for other reasons, especially flight reasons or piloting reasons.
Ted, I had a question for you as well that is coming in from the Q&A. For this particular flight, I see in your Wingtra pilot on the left-hand grab there, this one, I guess you flew this with the RGB 61 and the LiDAR. So this was approximately a 9-minute flight.
Yeah, approximately. Yeah, you can see here that the RGB flight was about the RGB 61, the one that I have on the left hand there, that is just I built that to see what the difference would be between the RGB 61 and the RX1R. I actually used the RX1R. That's the one that I was given. Yeah. So lower resolution, more overlap, and I shot the RGB in at a centimeter GSD. And also, it was the day before the LiDAR flight occurred, and the wind conditions were a little bit different. So you can see that the direction of the flight was different because of that. And that's one thing with VTOLs that you kind of have to think about. Whereas with multi-rotors, you forget about the wind because they kind of just power through it. VTOLs, I wouldn't say are very, the wind speed is super critical. It definitely can be, but it's not as big of a deal as I imagined it would be, but you still should consider the flight direction with respect to wind. Once we have the data, I mean, here's a direct comparison between the photogrammetry version of it and the LiDAR point cloud, right? So with photogrammetry, it's pictures. So we have color, we have pixels, and we can create a point cloud at almost infinite density. We can really just choose whatever density we want to extract those points from the pictures from. With LiDAR, we don't have RGB, but we have intensity. So that essentially is a measure of how powerful the laser pulse was when it came back and was detected. So, basic principle of LiDAR is that there is a laser emission and then a detection of that laser after it bounces off an object. So if that object is reflective, then the return pulse will be, will have quite a lot of power, and that is how we get to this grayscale image that basically shows us what RGB shows us, but in one color palette at a time. Both create point clouds, though. Point cloud is a point cloud is a point cloud. Doesn't really matter how you created it, and it's just a series of points in space. The big difference, though, as you can see, the photogrammetry side is on the left and the LiDAR point cloud is on the right. So the things that stand out to me here, first of all, is density. It's pretty clear that photogrammetry will win in that category because you can choose what density you want. LiDAR is a constant emission of points. So if you're moving quickly or if you're moving slowly, that's really the only way to control that density. But there's a lot of missing information on the photogrammetry side. None of those trees were captured at all. And most importantly, you can see the gaps in the area below the trees there. And you'll see with LiDAR that is very different. This happens in photogrammetry just purely because we can't see. We can't measure what we can't see. And so you can imagine, every photo taking, a perspective like this. You can see the thumbnail of the photo there, and that green dot in the middle would be where the camera sensor position was. You can see photogrammetry, we're just tracing a ray of light through that photo into the world coordinate frame. And where we can't match with other photos, we can't triangulate a point. So even in leaf off season, which was what this was, not a leaf on those branches, but there still isn't enough matchability essentially between those areas to fill them in. So this can be problematic if you're surveying or you're mapping an area with a lot of vegetation, a lot of change in that vegetation type. Another situation where you begin to see the shortcomings of photogrammetry, and trust me, I love photogrammetry. I'm not knocking on photogrammetry. It's definitely my favorite way of capturing reality, but it suffers when it comes to thin structures. So you can see this distribution pole on the left, and that's very clearly there. It's there in many photos. However, in the point cloud, it does not appear. It was never reconstructed. And that's because it just doesn't have that much area with respect to everything else on that picture, on that image, to account to be matched over and over again and be chosen, I guess, selected to be reconstructed. If you look at LiDAR on this example, it's a completely different case. And that mostly is because of the number of returns, but then also that these returns are discrete returns, right? There's no triangulation, there's no matching that needs to occur. We just know where the laser scanner was. So if we know where it was, we can map out where all of the points it found were at that time, and then just go through the timeline. So you can see in this image the three returns and how they kind of operate through a canopy. The white points are the first returns, the orange points are the second returns, and then finally we have the third return. And you can see all three make it to the bottom, to the forest floor. But if the canopy is denser, then you may not get the first return down there. You may not get the second. You still have a chance with a third. And so that's a huge benefit, and it makes a really big impact when you're working in these larger areas. You kind of don't have to think about the terrain you're mapping when you have this. Compared side by side with photogrammetry in the same area. So you can see photogrammetry can make its way through. We can get some ground hits, but those ground hits are not guaranteed to be accurate, especially in these conditions. They may be picking up a twig, it may be picking up something of high contrast that's just slightly above the ground, and it's very hit and miss. You can definitely optimize for it, and there's things you can do. But at the end of the day, it's not the right tool for the job. And then here's that example of the distribution pole and those wires. You can see that photogrammetry in some cases was able to get, a part of that wire to reconstruct. The ground is not a problem, but the rest of that structure is completely obliterated, right? There's nothing there. So it really just depends on what you're looking for, and always using the right tool for the job. And as you'll see, the applications where you do need to see the wires in LiDAR work are quite vast. So this is very useful to have, even if you're not specifically looking for it that day. Now, in terms of accuracy, I'm not going to go too much into the accuracy validation here across the three platforms. I'm going to save that for a deeper dive on just that topic, because I think it deserves, an hour on its own. We had about 35 control points that we used to check across this site. But the one thing that kind of does need to be mentioned is the difference between LiDAR and photogrammetry in terms of precision. So these are 2-point clouds that we were just straight out of the photos or straight out of the LiDAR sensor. And so you can see the difference in terms of photogrammetry. The points that are gray and green there, the lighter ones. They're very dense and very close together, very precise. Then while the LiDAR points, they can be a little bit more spread out, right? So on hardscape, on areas like curbs and roads, things like that, LiDAR is not going to be as accurate as photogrammetry. Photogrammetry done well, that is, right? You can definitely have poorer results with photogrammetry if you're not being careful. But fundamentally, there's more information there to tie from. That being said, right tool for the job, right? If you are using LiDAR, chances is you're not going to be using it just to go out and draw out these curbs and get the line work off of them. You're using it for much larger areas and areas with mixed terrain types and vegetation types. The real magic starts to happen when we classify the points, though, and this is my favorite part of it. This is, again, in LiDAR 360. This used to be really difficult. Classifying, for those of you that may not be familiar with the topic, is the act of essentially assigning each point an attribute. So, a point that is that was from a tree, classify that as vegetation. A point that's hit a vehicle and bounced back to the sensor, classify that as car. And so you're seeing these layers kind of peeled away within that data set. And this is where everything kind of starts to come together, and all of the value begins. Like I said, this used to be very, very manual. A lot of a person in front of a computer screen clicking for long, long hours.
How is this done today, Ted?
Today, it's I think we're starting to see, it's still early, but we're starting to see huge improvements just due to the AI and machine learning aspect of how that can be applied to this. And so this is results from LiDAR 360 that I got with one click. I literally clicked classify with machine learning, hit OK, and then waited about 10 minutes. And I did no other editing. There are definitely some errors, but if I can get it 95% of the 95% of the way there, I can, I have no problem cleaning those errors up manually.
And Ted, now you have shown us how to fly the drone, how to collect the data, how to classify it using AI. And as a construction company, what could I do with this data?
Yeah, well, generally, the thing that most LiDAR users are after when they're planning a mission with LiDAR is the terrain. They want to get an understanding of what the terrain in the area is, right? So a topographic survey, essentially. That's where this classification starts. That starts you on that path. So we need to pull out the ground points, the points that represent the mean elevation of the ground across the area. So once we have those points classified, then we can start working with those clouds. And so the first result, right, the most common would be this digital terrain model that I have here. And I'm actually flipping here between the digital terrain model, the DTM from the LiDAR dataset and the photogrammetry dataset. So I think you'll notice where they change, right? It's in those areas that had all of that vegetation that you'll see these gaps and these holes essentially in the RGB dataset. Whereas the LiDAR dataset has a very nice and even continuous contour. from a surveying, construction engineering standpoint, this is probably going to be the first thing that, the first data that's collected from a location before that work begins or that planning begins. And there's many, many more applications where this information is very useful. Floodplains, watersheds, right? And a ton of environmental situations where this is just this first layer of data here, just a few clicks in, is extremely powerful.
What about contour lines? Where do you get
Yeah.
the
Yeah,
you have them there.
good timing. So the contours that kind of show the same thing, right? One of these is contours from the LiDAR data set. The other one is contours from the photogrammetry data set. So you can see the irregularity of the blue ones, I think, right? That kind of gives it away, especially in that area that was vegetated. There's a road on the left there. And in the LiDAR data set, the purple, you can see those contours at that edge, white, very, very uniform, very consistent throughout. But then on the photogrammetry data set, you see some weird stuff happening with these contours, some very short ones, some peaks in areas that probably aren't there. And so it's all about that consistency across the entire survey that really matters. And then add in the efficiency that this is collected, right? The comparable version of this is doing it manually on foot, traversing through that with a total station or with a GNSS receiver if you can. You're going to get 1 point maybe every 10 yards, depending on how the survey crew operates, and you could be there for a week. Or you could scan it with LiDAR and be done in 8 minutes and 2 clicks in the office, and you're at this stage. So the quality level is quite impressive. And again, when you use the right tool for the job, everything just falls together. There was a bit of construction happening at this location. So this location is right on campus at our college here in London, Fanshawe College. And so we were flying this on the weekend, and it was actually a very windy day, which initially I wasn't super excited about that. But then as I got there, I'm like, hey, this is like a true stress test now, because we know it's going to be fine when it's not windy, but how's it going to turn out when it's super windy? And so we scanned a large area, and in that large area was some construction. So here's an example of calculating a fill volume, right? So I drew a simple polygon over that ditch, and because all of the data is there in the point cloud, it's just a matter again of hitting compute and getting the volume that is required to fill that area to that level. And you can see here it's 2,400 cubic meters.
So this is an actual use case that an earthwork contractor could take and calculate the volume that they need to fill before even the work starts.
Absolutely. And this really starts to shine when it's done repetitively, right? And over and over again on the same location, because you can see that change very quickly, very easily measure it. At the end of the day, it's accountability. It's also safety and progress monitoring. So there's so many of these situations that I haven't even encountered, but our users are putting this data to work in every day. Here's another site. This was a large aggregates pit. This was about 20 minutes of flying. You can see the lines, the trajectories there. Quite a large area. I was with a surveying company there that day. I was helping them, but I also had the Wingtra with me, and I said, "Hey, you guys are doing this with photogrammetry. Can I bring this LiDAR drone and give it a shot and see what the difference is?" So this large site, if this was done manually, they told me this would have been about 2 weeks of work. And so their task was to measure all of the volumes in these piles. The real sort of wow moment happens when you see the amount of vegetation that was on these piles. And then thanks to that classification, right? Just classify ground, get rid of everything that's not ground, and that leaves you with the bare terrain, bare earth model. And from that bare earth model, we can again measure those volumes very, very quickly. And then if you're doing this once a month, once a quarter, you really only need to do this once you have the locations that you're measuring, and you can compare them over consecutive data sets. Everything will just fit right in. LiDAR doesn't work with ground control points like photogrammetry does, right? So you set your base up and you fly that mission, and everything should line up if you set the base up correctly. So there's, the efficiency really starts to grow when you get into these situations where you're at the same location multiple times. It gets progressively faster each time, essentially. And you can see here, just drawing a polygon, choosing the grid. Here it's 2-meter grids that are being calculated and hitting compute. And we have the volume. And you can choose, how granular you want that information, because there's more information there than you could probably ever want in terms of resolution. And so it's just a matter of, how much time do you want it to calculate for? And it's usually very quickly. I did all this on my laptop, by the way, so it wasn't even something that requires a extremely powerful computer to do.
Did you also do this with LP360?
LP360, no, I've never used it. The thing about
Sorry,
the
LiDAR
LiDAR,
360.
yeah, LiDAR 3, yeah, so everything you're seeing here after correcting that trajectory is LiDAR 360. I really love that software because it's just so simple and so easy to use, and it just works really well. Has so many options just in one package. But there's a few choices. I mean, there's a lot of great software. TerraSolid is I've heard great things. There's LP360, which you just mentioned as well, and they all have their pros and cons. And it's just a matter of using the one that fits your workflow the best, and maybe the one that you purchased a license for, because they this isn't free open source software, but it is software that really makes all of the value extractable from this information. One of those things in LiDAR 360 that blew my mind when I first saw it is this, right? So we're going back to that original data set. And I've classified the ground, but now I'm able to extract the trees individually. So this is a segmentation of each individual tree. And this is a very powerful tool in forestry and any sort of environmental monitoring. This is only going to get more and more important as our climate is something that we need to keep an eye on. So this again is one of those examples of when you have good data and you have the right tools, including the right software. It's one click and you get to this stage. Again, it's not 100% perfect. If you want to get it to 100%, it does need some quality control by a human. It always will, but it's so much faster than anything else and what was previously required.
And that some people are asking, what density can you get with LiDAR?
Yeah, so on that very windy day, I saw a density, I believe, of about 150 points per square meter. Now, what density can you get is a very difficult question to answer, because it really
it's not only
varies.
construction, it's also, I can see forestry, where these applications, this classification can be used. Can you tell us a bit more about the use cases in forestry?
Yeah, so tying into that density question, it's probably more important for forestry, to have more density than it is for construction or engineering. The density is a function of speed, essentially, and that relates to how you plan. In this data set, this is another area. This is one battery with the Wingtra. I was set up near the on the left-hand side there. What you'll actually notice is that this was half of the flight was one set of lines in one direction, and the other half was a crosshatch. And I wanted to evaluate sort of what impact does more dense points in an area have on this algorithm and this way of extracting these trees. And you can see the trees have been extracted across the entire data set. It's not really that dependent on that density at this point. Here are the seed points. So the location, the very top of each tree shown just by discrete points. You can see that classification and the seed location, the seed point there by each tree. And those colors just represent different trees. So it doesn't represent height or anything like that. We get very used to working with these different color scales in this type of data. But again, this is all automatic segmentation with LiDAR 360. From all of that data, though, you get a ton of metadata about each tree, right? And this is where what you would take and plug into specific formulas, specific tools used in forestry, databases, GIS, right? So you can see we have an ID for each tree, a unique identifier, and then we have a position for each one, an X and Y and a Z. We see tree height on that field. We have diameter at breast height if it was able to be computed, crown diameter, crown area, and crown volume, right? So all pieces of information that have their own purpose. And someone in the forestry industry, when they see this, they'll know exactly what they can do with it. But the real kicker here is just how this was collected so quickly and then arranged and structured in this format very easily, essentially.
Also, Ted, for like such purposes of like mining reclamation, after they're closing up the mine and monitoring the vegetation, what are your thoughts on, that application for tree counting as well?
Yeah, I mean, I think that makes complete sense. The question of how else would you do it, right? You would go through on foot and survey this, a more traditional style that may get to the point where it becomes so cost prohibitive, that maybe that's ignored or skipped, and this, really important information, it's not being followed through on. It's tough to say. The reality is though that any data is better than no data. So, while this may not be 100% accurate, it is certainly way better than traditional workflows if you just need a snapshot, and then you can choose to do more specific surveying or more specific analysis in select portions of this data set where you find something that's intriguing, right? So there's always going to be some ground truthing involved. But I mean, here LiDAR is, I think, a perfect tool in that situation because you can use it on the mine itself, on the pit, and get the topography and all those other use cases that I showed earlier. But then you still have it for this type of application as well. And you can always combine photogrammetry and LiDAR if you want a colored point cloud. It's just a matter of collecting an RGB version of the data set, a photo version, and then the LiDAR version, and bringing them back together. And software like LiDAR 360 can help you do that.
But may I ask how was this? It looks like a picture, but we know it has been a trajectory of sweep. So may I ask how has this been captured?
Yeah, so you can see the trajectories here, right? So like I mentioned, there's two sets of lines. This is one battery. I wanted to see how much I could get out of one battery, but then also, with this location being so densely vegetated, I also want to see what the difference is between one flight and a crosshatched flight, right? So you have that option. If you want more density, add another layer of trajectories in there, right? Add another layer of points. The result is, it wasn't that surprising. It's basically double the points. It's almost exactly double the points when you have a crosshatch like this. This area is just under a square kilometer. And this was flown at 80 meters above ground level, using the terrain following. So that turned out to be about 30 minutes of flying, I believe. And when you look specifically at those points that were generated from the trajectory, you can kind of see the area where there is a cross between two flight lines. You can see that there's more points there, right? It's a lot brighter. I'm using the glass shader here to display this, so it is a little bit different than typical point cloud rendering, but it really brings out that difference of more density in that area where two flight lines intersected versus the blue line that came across. And when we look at the profile here, I'm switching between one line and two lines, so you can see the amount of points basically doubling as I go through this. So the final thing to say to add into here is that the post processing can really take whatever whatever complexity you want it to, and especially with aligning these strips together. What I found is that from the LiDAR on the Wingtra, that payload is quite well aligned strip to strip. And I think that the strip alignment is optional. It doesn't provide a ton of added accuracy. It definitely is a case by case basis. But in a nutshell, I think you can just cut by overlap and then get to the same results quite consistently. And again, I'll have a lot more a much deeper dive on just the accuracy and the benchmarking of these systems together.
Now,
Right.
I have a quick
Mhm.
question for you as well. Typically with the Wingtra LiDAR, kind of out of the box, we suggest to fly right around 300 feet. Is that what you
Mhm.
flew this mission at as well? What was your AGL? Do you recall?
So I found the sweet spot to be around 80 meters, 80 to 90 meters. If I switch back here, this is typically what I flew these at. Um, there's a few things to keep in mind. First of all, obstacles, right? So you don't really gain anything by flying lower. And there may be obstacles, so why even bother? But you also start to lose returns as you fly higher, right? So there's this thing called the probability of detection. So the LiDAR scanner, it's emitting a pulse of light and then it has to detect it. So if it's detecting something very faint or something that it perceives as false, it will just discard that information. So as you get higher, that probability of detection starts to decrease, and you have less of a chance to get those third returns, those second returns, etc. So I found that 80 meters is where I preferred to be. It's well above any obstacle. It was a sweet spot between accuracy and efficiency in the field. And I can't really see a situation unless I really want to cover a very large area and I want to do it very quickly to fly at 400 feet or the maximum altitude that you can fly in your area. The scanner, the laser in this payload, though, I mean, on the spec sheet says it's good to like 300 meters, so well above what you would be flying a drone typically. But that doesn't mean that you need to be flying that altitude, or that at that altitude it will be the same kind of results that you see at the 80 to 90 meter.
Could you talk a little bit more about the strip correction? Did you do anything extra, anything else special for the strip correction when you were
Mhm.
processing?
Yeah, so I process these with two versions essentially, and when I after I present the results, I'll make all of this data available,
Mhm.
including the raw, like straight off the sensor, aligned once, and then also my final sort of best I could get it to for all four of these platforms, so people can go and dive in themselves. There's no ambiguity there. The strip correction, though, I found to be I'm always going to do it. Because I work with this data all the time. I find it very straightforward, very easy to do. It's a few clicks and a little bit of waiting. So I typically would recommend it. But I found that it's very marginal in this case. It's only at the very extreme ends of the swath. And then also keep in mind for this day, we had extreme winds, like right at the edge of what the manual said we couldn't take off with. I mean, who knows? Maybe we did break the manual rules a little bit. But that's where I saw this kind of deviation from swath to swath. Overall, it's on a case by case basis, though, right? If you want the utmost accuracy and precision from your data and you need it for what you're doing, do that strip correction and do that strip alignment, do the cutting. I think the cutting is also one of those things you can probably skip if it's a forestry data set, right? Or if it's a more of an engineering use case, more of a survey use case, you definitely should be cutting and aligning. But again, everyone has their own workflow, and I think every tool is also slightly different in how straightforward or how easy it is to get to that strip alignment and how much effort it requires.
And another question we have is particular to the slide that you had with the grayscale imagery.
Mhm.
The car seemed to be missing in the one in the one picture. Was that
Mhm.
just because they were done at separate times?
Yeah, they were done 2 days
Yeah.
apart. Or 1 day apart. So this was Friday and the LiDAR was on Saturday. And the reason for that is because on Saturday's session, we had a lot of LiDAR flights to do. If I can go back to this slide, like we had the Wingtra, the Quantum, the Delta Quad all on the same day. And we had to, make sure that logistically, we didn't have any interruptions. And so, the thing about LiDAR is that it really doesn't depend on lighting at all. You could be flying at night. In fact, I think you probably see slightly better results at night, maybe some more, that probability of detection being higher. But with photogrammetry, you have to have good lighting conditions. And as you can see on the Saturday, it was very overcast, and the day before was a beautiful sunny day. A lot of light entering that camera, fast shutter speeds, and I got some pretty incredible results in terms of accuracy from the photogrammetry day as well. I was really blown away by that. First of all, further sort of reinforced my love for photogrammetry. But again, that's the only reason you see two separate sets of cars in the parking lot. The same base station was used, same location, same controls. And so I think it's a pretty comparable result.
The slide with the contour lines,
Mhm,
particular to the roadway,
mhm,
since there would be no obstructions on the roadway,
mhm.
why wouldn't we expect it to be a little bit closer or more similar? Why does the LiDAR data show a little bit better, in your
Yeah,
opinion?
the question is like, who's right? Is the LiDAR correct or is
Mhm.
the photogrammetry
Right.
correct?
Yeah.
Right? Like, don't know. We don't really know. Even if we went and used a GNSS receiver to shoot some points on there, is the GNSS receiver right? I mean, vertically, GNSS can be off by 2 centimeters easily, right? So that can, when you're looking at contours, very fine contours like this, these are 10 centimeter intervals. Even a small little undulation can make a difference. I would suspect that the contours on the LiDAR side are a little bit smoothed out, just due to the fact that the precision point to point is less. Like there's a little bit more gap between the points. So when the contour is being generated from that DTM, there's a little bit of a sort of smoothing occurring inherently there. Um, the reality is that if you were doing a survey and you wanted the ultimate contours from that roadway, then you should probably use photogrammetry and you should probably plan the mission specifically for that, not a very large area like I was doing here at a centimeter GSD, right? You would want to increase or decrease that GSD in those cases.
And Ted, I have another question from the audience that actually links to this topic you were discussing. And it is for large solar fields that are being built where topography is the goal.
Mhm.
Which technique would be preferred to capture data, photogrammetry or LiDAR?
So you mentioned soccer fields.
Solar fields.
Okay. Um, I think if it's very large, I think LiDAR would be my go-to. But I think these types of questions all hinge on, what is the terrain in the area this solar field is being built on? Is it vegetated or is it a solar field in Utah? That's desert. Um, Start with that question first, and then second question would be, well, how much area do we need to cover, and how much time do we have to do it? So in this on the photogrammetry side, controls, of course, are going to play a pretty big role there. Of course, you can PPK your data and just do a few checkpoints. But if you want the best results, you should have a minimum of 30 controls across the site. With LiDAR, those controls are still valid. You should have them to check against, but they're not really gonna be used to influence the reconstruction, because the whole point of this is that we know that trajectory is very accurate to begin with, and that's what you're paying for. You're paying for that hardware inside of that sensor, the IMU, and the GNSS receiver inside of there to be of the highest grade and the highest quality. And that is essentially what determines the accuracy. And then the laser determines your efficiency, right? You can cover huge amounts of area, regardless of the terrain cover, and get really good, really consistent data as well.
What does a company need to start harvesting the benefits coming from aerial data collection with LiDAR?
So I would say that you need a sort of a good understanding of geospatial information, right? It's the drone is the tool, it's the field tool, but a lot of the magic happens in the office on software. So it can be really daunting and feel very, very complicated. If you don't have a good foundation to go in. But in terms of hardware, what you need, essentially, in this case, I just required to have a GNSS receiver, a base station, and the Wingtra and the drone, right? So those two things are really it. Of course, there's levels, right? There's going to be additional things logistically that may help, but you can start out, quite quickly, especially if you have someone within the company that can be that superstar and champion the whole thing. What I see most often when this doesn't work out within large organizations is that someone that maybe has other tasks or a different role within the company, it doesn't specialize in this type of work, is given this responsibility and they're not given the support to handle it, because you do need to keep up with it. It's it's a bit of an art and a science, and it's something that you will get better over time. And so when someone isn't given that support and confidence, then you can have suboptimal results that may reflect poorly on the hardware and the software. But it really is just a matter of taking the right steps and doing it right the first time.
If you were in an urban area, what would be the preferred method of data collection, LiDAR or photogrammetry? Like, to me, I know a couple things kind of pop in my
Yeah.
mind. Is this a pre-construction survey? What are we actually trying to do?
Mhm.
What's the vegetation, right? Like that's always
Mhm.
kind of the starting point. If we're talking bare earth or just roads or
What do you need the
buildings,
data
LiDAR is.
for?
Yeah.
Mhm.
But
Yeah.
the urban environments are interesting too, because just like you were able to color code your trees, say you were trying to do a fire hydrant count or something to
Mhm.
that extent, LiDAR could be very useful for something like that. It
Yeah.
just all kind of depends.
I think, yeah, you're absolutely right. It definitely depends on, what is the derivative that you
Mhm.
want from this data. First of all, what are you looking for? Like I have
Agreed.
a startup company that what we do is count vehicles parked in parking stalls, right? From aerial images. We could do it with LiDAR, but it's just simpler to do it with photos, right? And there's
Yeah.
additional information in the photos, such as the car color. We can kind of track that car over time. Um, but if you're mapping and you want to pull out how many trees there are on this block or sort of the building outlines, you want to pull out 3D models from them, LiDAR works great for that. Generally, LiDAR will be more consistent in the point cloud. So this classification, like I showed you here, it just depends. It's looking at the shape of the point cluster, right? It's just looking at the geometry that those points are creating. So if you have consistently realistic points that match what that object is and what the labeled information that created that model was, you're going to have much better results with this type of workflow and this automatic classification. So I think that would be really the winner in terms of the urban setting. But again, I think both are equally valid. It just depends on the job and the tool that you need for it.
Mhm.
It really depends on what the data is going to be used for. For example, we see a lot of usage of photogrammetry for cadastral applications. So to map a
Mhm.
city for a cadastral map, you don't even need a very high resolution. And that can be achieved with an orthomosaic model. Also, 3D models captured with an oblique camera are very useful to that, not only to see the, let's say, the orthomosaic, but also the 3D shapes of the buildings, how many
Mhm.
stories do they have, and so forth.
Mhm.
So yeah.
Yeah. Yeah. Exactly.
And Ted, and we are actually soon to wrap up. We have about 2 minutes left, but I have a follow-up question from the audience on this whole topic. And many people are wondering, okay, data collection with drones, they can see all the benefits from it, but can you give us a bit of insights? So when do you recommend using drones versus terrestrial methods for data collection
Mhm.
versus manned aircraft?
Yeah. Oh, that's a great question. I recently did a webinar with Skydio on the accuracy between photogrammetry and laser scanning. In that example, the laser scanner was a terrestrial laser scanner, and the photogrammetry was a drone. Terrestrial laser scanning is going to be more accurate, by almost an order of magnitude, more precise as well, just because it's on the ground. It's generally a much larger payload and much larger sensor. And it's also not moving in a lot of cases. But the efficiency is borderline horrible, right? Like you're not using that for its efficiency, you're using it for its accuracy and precision. And so drones and laser scanning fit really well in the sort of in between the manned, crewed aviation and, the city scale, large, state scale data collection that happens all the time and will continue to happen. It has tremendous value. And when you want more density or you want to pull out more specific information from that point cloud, the drone is sort of the perfect tool for that. And then as you get into really, macro scale, really, really small details, then you want to do that from the ground. And in some cases, you can combine all these three together. There's a lot of open information too. A lot of these aerial laser scans from crewed aircraft are available to use, and I use that all the time for planning missions. Right, if I want to know what obstacles are in the area, I open up that open source information and see, I can measure directly off that point cloud, the tower, the buildings, and then I can plan my drone flight in accordance to that. And so they all work very well together. And it's truly all about what you're looking for that decides which one's the best for you.
All right. That's fantastic. So we are just up here on time. Ted, I wanted to thank you again for joining us today and taking time to run the Wingtra through its paces. I'm really looking forward to seeing your final data reveal with all the aircraft and final thoughts with all of that. And Javi as well, thank you for joining, and we will see you next time. Thanks, everybody.
Thank
Thanks
you
for
very
having
much.
me. Take care.
Ted, it has been a pleasure learning from you. Thank you.
Same. Thank
Yes.
you.
Bye-bye.